Thanks everyone for coming to the first ESC PhD Colloquium of 2016. This year is going to be kicked off by Amin Rahimian, who did his undergraduate degree at Sharif University in Tehran, and then did his master's degree at Concordia University in Montreal, both in electrical engineering before he started at Penn, where he's been working with Ali Jadbabay for the past several years. So today, Amin's going to be talking to us about Bayesian learning without recall. So without further ado, Amin.
Thank you. So I will be presenting my results on Bayesian learning without recall, which is a joint work with my advisor, Ali Jadbabay. For the motivation of the work, there are several situations in which people exchange opinions with their peers in order to make decisions. For example, when investing in stock market, voting in an election, choosing their political affiliation, opting for a brand of a product, or on the best course of action in medical treatment. And in all these cases, you can single out a few possibilities that are available to the agent, and one of them is the best one. And in order to decide on the best option, people exchange opinions, beliefs, make observations, and these occur in a variety of media which we collectively refer to as social networks. And the problem of social learning, that is traditionally a focus of microeconomics, is to understand how these interactions in social networks will shape mass behavior and will influence individuals' choices. This problem is closely related to problems such as distributed detection that are concerned in engineering literature, and studies on them go back all the way to 1980s, and they still continue to attract attention. Some of them are listed here. The Bayesian approach to this problem of social learning is to apply the Bayes rule to the observations of the agent to make inferences about the problem at hand. But there is a fundamental drawback about Bayesian learning. That is that in order to make inferences about the observations of a neighbor, you have to consider all the contingencies that lead to those observations, to the actions that the neighbor take. And so you need to basically consider the observations of the neighbor that have led to an action that the neighbor has taken. And these actions are not available to you. And this leads to very complex inferences. Still, there are some features of Bayesian learning that can be handled, some analytical features, and there are studies that establish, for example, convergence results. But when you look at it computationally, it is a very complex task, doing Bayesian inference in a social learning scenario. The alternative is non-Bayesian learning, when agents rely on some form of averaging to aggregate the observations from their neighbors. They do not try to make the best possible or the most accurate inference or the most rational, or to make the most rational choice, but they rely on some kind of averaging rule to combine these observations. It is a form of a rule of thumb, and the hallmark of these results is due to de Groot in 1974 in statistical literature, when it proposes a linear combination as a way of studying opinion dynamics. When every agent puts his next choice equal to a linear combination of her neighboring choices, as well as her own. More recently, this framework has been extended to the case when, in addition to making observations about the actions of the neighbors, the agents are also receiving a sequence of private signals, and how to incorporate these streaming data with the previous linear combination framework. That's a study in 2012 by Jadbabay and others. So in our framework, which we refer to as Bayesian without recall, we try to drive these averaging rules in a principled manner. That is the main motivation for the work, because there's no reason why an agent would be following any kind of averaging rule, except for that it's a way to analyze network behavior. So there are no behavioral foundations. In our approach, we look at the Bayesian update of an agent at time 1 when it is still computable and we don't have this problem of hidden observations across the network that significantly complicate the inference task. So when the inference task is still possible, we can compute its format, and then we have a structure that is a form of averaging rule that we can repeat for future time steps. That is the key idea, to repeat the Bayesian update at one time step for all future time steps. And we argue that this is a behavior of a Bayesian agent that has no recall, because at every time step it is behaving as if it is again time 1. So it provides a behavioral foundations. Following this approach, we can drive many of the well-known existing averaging rules that are already in the literature. And also it provides a way for analyzing rational behavior subject to this constraint of no recall. So let's get into some modeling details. There is a true state of the world that is chosen from a set of finitely many states, and that is the state that agents are trying, that is affecting their decision. That's the principal object of learning. And at every time the agent observes a private signal about this unknown state, and it is distributed according to a likelihood condition on this true state. The signals that the agents observe are independent over time, so each agent is observing a sequence of IID signals, and they are also independent across agents, although signals of different agents are distributed differently. That is how agents are going to benefit from communicating with each other, because each of them are receiving a different kind of signal about the true state. And we suppose that the agents start from a full support prior belief about the unknown, and at every point in time the belief of the agent about the unknown is a probability distribution on this set of finite possibilities theta that we denote by mu indexed by the agent I and the time t. To each agent there is an action space that are the set of options available to the agent, and there is a utility function that rewards that action based on the state of the world. So utility function is a mapping from the action space and the state space to the reward of the agent. And at each time the agent chooses an action based on her belief, and that action is then rewarded based on the utility of that agent. So, following this approach, let's now implement this Bayesian without recall idea. At time 0, the agents observe a private signal. That is, each agent observes a signal about, and that signal is distributed according to a likelihood, Li. And then at time 1, agents exchange their actions with each other. So each agent observes also the actions of her neighboring agents. And based on the actions that she has observed, as well as the private signal, she can form a belief about the unknown, and then she knows the structure of her utility function, so she can take an action that maximizes her expected utility. So this action at time 1, AI1, has a functional form, and it is determined by the signal that the agent has observed, as well as the neighboring actions that she has observed from her neighbors. We take this functional form, and for all future time steps, we repeat it. That is the Bayesian without recall action update. This also constrains the belief of the agents in some way, because if they are going to be rational, they have to be expected utility maximizing. So This update, just by setting AIT equal the functional form Fi for all time t, we are constraining the belief that a rational but memoryless agent would be holding under these circumstances. Note that the agents, since they have no recall, they have no incentive to deviate from their myopic best actions, because any revelation that would be a result of deviation from the best action, they cannot benefit from that because they have no recall. In future they cannot analyze the consequences of a potentially false report. So this.
And do they know that they won't recall?
Yeah.
So then, why don't they write things down on paper? Why is it costly for them to recall?
The principal motivation for it is a behavioral assumption. Rather, so the recall is not rationally justified. The fact that they have no recall, there's no rational justification for the fact that they have no recall. It's a behavioral imposition on the agents. And the principal motivation is to drive those naive updates.
And what is the objective of the agent?
To maximize her utility, expected utility, given her observations.
Wait, but they're going to be doing this repeatedly over time, right?
Mm-hmm.
So is it the time averaged utility? Is it the discounted utility?
Some of the utilities you can, but any kind of forecasting that is a result of utilities that you're going to gain in the future will not affect the best strategy because of this without recall assumption. Because you're always forgetting the history. I mean, even if you consider a discounted utility, you would still get the same result as far as the form of the updates are concerned.
But if we do undiscounted and our agents are naive, why don't they just simply do nothing for a large number of periods, observe their signals, and then if they get enough signals, they will all know the actual state, and then they just choose the correct action for the state?
Thanks a lot. Yeah, that's a very good question. One of the main motivations is when the agents are facing identification problems. So there are states of the world that cannot be distinguished based on the private signals alone. For example, there are two states, and the likelihood condition on these two states are the same for one agent. Yeah. Still, if overall the true state is identifiable through the aggregate observations of all agents across the network, the agents can still learn under some circumstances. Okay. So now let's get a bit more specific about the settings of this modeling. As a first case, we consider a binary state and action space. So there are two states, plus and minus 1, and two actions, plus and minus 1. And the utility rewards the agents based on their guess of the true state. So if you correctly guess the true state, you will be rewarded by 1. And if you make a mistake, you will be rewarded by, you will be penalized minus 1. And just for the sake of writing things down, let's suppose 1 is the false state and minus 1 is the true state. And we label these states theta 1 and theta 2, and then there is the likelihood log likelihood ratio of the signal. To each signal that we assign a log likelihood ratio, that is the log of likelihood at the false state divided by the likelihood at the true state. So at time 0, you just have a private signal, and by applying the Bayes rule, it is easy to show that the optimal action, given just your private signal, can be expressed as a sign of the log prior ratio plus the log likelihood ratio of the signal that you have observed. At any given time, due to this utility structure, you will choose +1 if you think +1 is the more likely state, and -1 otherwise. So our first lemma extends basically this action at time 0 to an action at time 1. This time it will depend not only on the private signal that you observe at time 0, but also on the neighboring actions. So the time 1 Bayesian action under this binary state and action space and this utility structure is given as the sign of a weighted sum of the actions of the neighbors plus a constant eta I and the log-likelihood ratio of the signal at time 0. Before going further, let's analyze this update a bit. There's a constant eta of I. We can write this constant as two parts, sum of two parts. The first part is the log belief ratio. That is the log of the log of prior ratio. That's the log of the prior that you put on θ1 divided by θ2. So it is basically, this constant eta1 is basically expressing the natural tendency that the agent has toward action 1 without any observations. Part of it is due to her prior, and part of it is influenced by the knowledge that she has about the likelihood structure of her neighbors. So that is the second constant. And we can actually show that this second constant Vi here is for any fixed signal of any neighbor is increasing in the likelihood of that signal given the state θ1, and is decreasing in the likelihood of that fixed signal given a state θ2. So without having any observation at all, you still have a tendency towards some action just based on your prior and your knowledge. And this weights Wi depend only on for any agent, depend only on the likelihood structure of that agent. And it doesn't matter who is making an inference about the action of that agent. There is a single constant associated for example, agent J, that whoever is observing the action of agent J will weight the action of that agent by this constant Wj, because they are all rational agents, and given the same observation, they will make the same inferences. This Wj is completely determined by the likelihood structure of the signal of the agent I, and it is such that if it is larger, it is showing that agent I has a more observational ability concerning the true state. So the fact that it is positive shows the case of positive externalities. When more of the neighbors of an agent are making some decision, then the agent is likelier to make that decision, irrespective of her private signal. And it is also shows the case of observational heterogeneity across the agents in the network. In particular, we can have a case of expert opinions in the network when some agents have a very large constant Wi, and the actions of those agents would be shaping the mass behavior in a more central manner compared to other agents. So now let's go to analyzing the dynamics of this model. So after getting this update at time 1 and making the necessary substitutions, we replace time 1 by t and the actions that you have observed from your neighbors at time 0 by t minus 1, and you replace the signal by the signal that you have just observed. So you get an update that sets an action to the sign of weighted actions of the neighbors, a constant term, and the log-likelihood ratio of a signal. This update is very similar in structure to the model of an artificial neuron that is studied in neural networks and for computing, as well as the Glover dynamics in the Ising model, when these plus minus ones are representing atomic spins. So under this model, the actions are going to evolve as a Markov chain on the Boolean cube. So you put actions of all agents in a sequence, you get a sequence of n plus minus ones. these are the vertices of Boolean cube. And when you implement this action update, you get that the jumps between the vertices of the Boolean cube follow a Markov chain, and you can specify the probability for any given jump from a vertex to another vertex based on the likelihood of the signals. And there is a particularly interesting feature of this dynamics, that is the equilibria of this dynamics. That are, if there are some vertices that when you visit with probability 1, you will always remain there in all future time steps. These are absorbing states of this Markov chain that I was talking about. And given the dynamic, we can characterize these absorbing states or equilibria. This is the mathematical characterization of the equilibria. It is requiring that for all agents, the likelihood structure be such that they will not be basically overpowering the actions of their neighbors. So they will not, they do not observe any signal that is strong enough to make them contradict the weighted sum of the actions of their neighbors. That is what basically this condition is telling, and it has to be true for all I. There is a special case of equilibria, that is when we have a consensus. That is, all of the actions, all of the agents in the network are taking the same action, either all +1 or all -1. This characterization of equilibria leads to a characterization for consensus being an equilibrium, and this doesn't depend on the fact that whether it's the consensus are +1 or -1. As in order for any consensus to be equilibrium, we need, in an if and only if manner, this condition on the likelihood structure of all of the agents. Again, it is saying that the likelihood of no signal is strong enough to contradict the consensus among the neighbors. And this has an interesting consequence. So if the true state is -1, we would like a consensus sign -1, and we would like it to be an equilibrium, meaning that the agents reach a consensus on the truth, or they learn. But if that is going to be the case, the consensus on +1 would be also an equilibrium, because the characterization of consensus as an equilibrium doesn't depend on whether it is a consensus on truth or untruth. And based on the signal structure, it could always be that with some probability, you reach, if a consensus on truth is an equilibrium, with some probability you can also reach the other equilibria of the game. So with, whenever you learn with a positive probability, you also mislearn with a positive probability. And this is a consequence of the naivety of the agents when they are doing these action updates. This is basically the fact that they don't have recall. Because if they were rational, they would have enough data, each of them alone, to learn. And this is a well-established result for in the Bayesian framework. So these are all of the conclusions that we can make about this binary state and action space leading to an Ising model. So now we go to a more subtle case when the action space is richer and the consequence, and we try to analyze the consequences there. So here consider a state space that is finite. It's not just binary. We have impossible states. And the action this time, for action, take the probability simplex on these states. And for the utility, given any action and any state j, the utility is a quadratic that measures the distance between the action that you have taken and point mass on the state j, meaning putting probability 1 on the state j and 0 everywhere else. Subject to this quadratic utility, the action space being probability simplex and this finite state space, the actions of the agents, given their beliefs, are actually their beliefs. In other words, this action space is rich enough to reveal completely the belief of the agent about the true state. So what they are doing is actually at every time they are exchanging their beliefs with each other. Now, the time one Bayesian belief, given the private signal that you have observed as well as the neighboring beliefs, is given by this function that is expressing the belief that you have at time one as a function of your prior, as well as the signal that you observe at time 0, and the product of beliefs that your neighbors have reported to you. It is interesting because it has a linear form. If you look at the denominator as a constant and you take the logarithm of both sides, you see that the log of belief is set to basically sum of the log of beliefs of the neighbors as well as the log likelihood of the signal that you observe. But before going further with analyzing the dynamics of this update, let's consider a simple case. When we have just a single Bayesian agent, this is very easy to write down the Bayes rule for this agent. It is just the likelihood of the signal that she observes timed, multiplied by the belief that she had, and then you just get the Bayes rule at every time step. To analyze the evolution of belief under this update, you can form the log of the belief ratios between the belief that you put on a false state divided by a belief that you put on the true state, and then you take the logarithm of both sides. You see that the log of belief ratio that we here show by phi evolves as the sum of the log of belief ratio at the previous time step plus the log of likelihood ratios. And when you iterate this summation over time, you get that the log of belief of this single Bayesian agent at every time is equal to the log of prior ratio that she had at the beginning plus the log likelihood ratio of all of the signals that she has observed so far. And if these likelihoods are such that they are integrable, that's an assumption that we make, and this sum is actually a sum of IID variables that is going to converge to its expectation, and the convergence is almost surely. So we get that this sum converges to a constant term plus t times the expected value of this log likelihood ratio. But the expected value of log likelihood ratio is exactly the KL divergence between the likelihood of the signal that the agent is observing under the true state and the false state. And this KL divergence is positive, and if it is strictly positive, then this expectation, that is the minus KL divergence, would be strictly negative. And this log likelihood, log belief ratio of the false state to the true state is going to converge to minus infinity because it's t times this expected value. So as time increases, the agent rejects the false state in favor of the true state because the log of belief ratios are going to converge to minus infinity. And since we took the logarithm, this learning rate is asymptotically exponentially fast, and the rate is actually this KL divergence. So the KL divergence is measuring the quality of your signals, and it's very natural to get it at the rate of learning. Here is an example of a single Bayesian agent with 3 states, and as she observes more and more signal, she would reject the false states 2 and 3 and put all of the probability mass on the true state, let's say state 1. So now that we have this framework of analyzing belief updates, let's get back to the network update. After making the necessary substitutions in the update that we derive for time 1, we get that the belief at any time t is equal to this update which has a multiplicative form. You take the prior likelihood of the signal and the beliefs of all of the agents. A main result here is that unless in a strongly connected social network, unless the spectral radius of that network is 1, this update cannot converge in a probabilistic sense. So to see how it is proved, it is very similar to the analysis that we saw for a single Bayesian agent, but of course we have to extend them to a network case. So instead of working with the log belief ratio, we look at this weighted log belief ratio of all of the agents, and the weights are the centrality of those agents. That is the vector of centralities, that is the unique eigenvector of the adjacency matrix corresponding to its largest eigenvalue. Since adjacency is a positive matrix, it has a unique eigenvector based on the Perron-Frobenius theorem. And we suppose that they sum to 1. And all of the entries of this vector are strictly positive in a strongly connected network. And similar to this, this is a network-wide global kind of belief ratio. And similarly, we have a global likelihood ratio of the signals, that is the weighted sum of log likelihood of all of the signals that the agent observes, weighted by the centralities of those agents. If you concatenate the beliefs of the agents in a vector and multiply both sides by this eigenvector corresponding to the largest eigenvalue of adjacency, we can basically analyze the update that I had written and you get this kind of evolution for the global belief ratio. It is again sum of IID variables, but this time these variables are weighted geometrically by the spectral radius. And that the geometric weight is what prevents convergence for these random variables when the network spectral radius is strictly greater than 1. Because you get a random variable that is being multiplied by a number that is increasing to infinity, so the variance is unbounded and there can be no convergence unless the spectral radius is 1. But for a strongly connected social network, the spectral radius of 1 means only one thing, that is directed circles, because the spectral radius is lower bounded by the minimum degree of the network. If it is 1, it means that the minimum degree of all of the agents have to be 1. Is upper bounded by the maximum degree as well. So for the case of directed circle, if the agents start from a common prior, then or even if not, the analysis would be quite similar, but to get a cleaner answer, suppose the prior that the agents are starting from is a common prior. Then they cancel out from the update that I had written, and for a case of directed circle, which we know the update is convergence, what we get is something very similar to the Bayes rule, except that instead of using your own belief, you're using the belief of your neighbor, the reported belief of your neighbor in the update rule. And so to analyze it, you can successively replace for the neighboring belief. For example, starting from agent 1, you know that the update of agent 1 is the likelihood of signal of agent 1, multiply the belief of agent 5, and then the belief of agent 5 is the likelihood of agent 4 times this is the likelihood of signal of agent 5 times the belief of agent 4, and so on until you come back to agent 1 in this example. And so at the end you get a Bayesian update that has only the belief of that agent, but with the likelihood of every signal in the cycle. And a similar analysis, similar to what we saw for a single Bayesian agent, applies here. And the rate of learning is this time given by 1 over n, when n is the size of the network, multiplied by sum of the K divergence of their likelihoods. So it is basically average ability of them in making their observations. That is the case of a directed circle. We know if we go beyond directed circle, we don't get convergence with that update, but there is a way to extend this update rule that is specific to directed circles to general strongly connected networks. All that we need to do is at every time require that the agent chooses only one of her neighbors randomly. We can put these probabilities of the neighbors that are being chosen into a matrix. So each row indices the choices of one agent among her neighbors. And we require that this probability matrix have the same structure as the network. So all of the neighbors are chosen with some probability. No neighbor is left behind. And that is enough. If you choose the neighbors randomly and then apply this rule, this circular rule, you will get convergence for the beliefs of every agent to a point mass that is centered at the true state. And we can again show an asymptotic rate of convergence, but this time instead of converging with the rate that is the average of KL divergences, it is a weighted average. And the weights come from the stationary distribution of that probability matrix with which these choices are choices of neighbors at every time is made. The way this result is proved is similar basically to the way we prove it for a directed circle, but instead of moving along a circle, this time we move randomly across the whole network. And this reduces to a random walk on the directed graph, and we can analyze using the ergodic theorem, we can analyze the long-run average behavior of the proportion of time that this random walk spends in each of the nodes of the network. And as this random walk touches every node, it's going to take the likelihood of the signal of that node at that particular time. So in this way we can prove the convergence result and how over time, following this approach, the agent is accumulating the signals from all of the agents across the network. And there are some theoretical features that are of interest. For example, unlike many gossip algorithms in the literature which require both a periodicity as well as a strongly connectedness from the matrix P here, since the proof only uses the ergodic theorem, we don't need a periodicity for P anymore. The directed circle is a best example. And still this almost sure convergence is going to hold. So to recap, we offered the replicating Bayesian update at one time step for all future time steps as a principled way for driving naive updates. And following this principle, we have been able to drive some well-known updates, for example, weighted majority and threshold rules, and log linear belief updates. In each case, we analyzed the dynamic behavior under that update rule. In the case of binary state and action space, we saw that actions evolve as Markov chains on the Boolean cube, and we characterized the equilibria of that Markov chain and what they imply about learning. And in case of the log linear belief updates, we saw that beliefs do not converge unless the spectral radius is 1, because we had a case of uncertainty accumulating over time. And the learning for the special case when the spectral radius was 1, we analyze the update in a directed circle and we get the learning rate as the average scale divergence. And for general topologies, there is a way to use to basically recycle that update for directed circles and again get a learning rate that is a weighted average of KL divergences. Thank you for your attention.
You characterize the learning rate in these two important cases. Is that in some way, it looks like that probably should be approximately optimal. Is that true? Can you say something about the lower bound on the, is there a bound on the learning rate and how this relates to it?
Yeah, that is a good question. I don't know any result for learning in such scenarios that is faster than asymptotically exponentially fast. Of course, there are also results that are more precise in the sense that they characterize a finite time. This result is only an asymptotic rate, because when you look at the log-log-active ratios, this is the almost sure limit of the log-log-active ratio. So there's a random time after which it gets close to this rate. So there are some results that characterize the finite time convergence in the sense that with a high probability, after some fixed time, not a random time, what is the performance. Those results are more precise and more computationally valuable.
So could that maybe tell you something about what you lose by not taking a piece of paper and recording, by making this assumption of no recall? Could you maybe show that quantify the trade-off that you make?
Actually, not having recall in the sense of rationality doesn't necessarily decrease the speed. It could be that, and there are some evidence to show that when an agent is making a rational inference, if they these sensitivities to the reports of others as well as her observations is actually somehow slowing down the learning process. So, and the current the analysis that I referred to are all for some kinds of averaging rules. None of them is analyzing the actual rational update because, as I said at the beginning, it is not tractable. There are no known computational methods for actually forming a Bayesian belief given all of the observations that you had so far.
Okay, can you thank the speaker one more time?